So what we're going to do is we're going to prove that 2n raised to the power of k is big O of n to the k for k is greater or equal to 0. So we're going to be talking about a polynomial that looks like that. Well, like this, n to the k. Sorry, I'm getting really excited here. So let's do this. So we're going to prove this. So recall this is the property, the second property of a function being smooth. If I can prove this, and I know a polynomial like this one is asymptotically non-decreasing, then I could say that the function n to the k is smooth. So to prove the claim, what do? It's a big O statement. I just have to find those two constants, right? We find constants. We find constant c, so the positive real number c, and n0, which is what? It's a positive integer. Positive integer. Such that for all n greater or equal to n0, it must be that 2n to the power of k is less than or equal to c times n to the k. So I'm just putting it in directly here. Remember, I just put wherever I had an n originally, I put 2n on the left-hand side, and I just leave the n on the right-hand side. So remember, just think of it like two different functions, just one with the 2 and one with just itself. But it's really just the same function we're talking about. So I just substitute in 2n. Okay. Now, this is where it's going to get a little strange at first if you don't know much about exponents. So I'm going to pick a very strange constant for you that it's going to look a little strange at first, but you need to remember that this constant k is in fact fixed. So whenever I talk about a linear function, I'm talking about when k is equal to 1. It's a constant when k is equal to 0. It's a quadratic when k is equal to 2. But you would agree with me that it's this k here is actually in fact a constant. So I'm going to use that fact. So let's do that. So I'm going to pick, now this is going to look a little strange at first, but I assure you it's going to all work out. So I'm going to pick c is equal to 2 to the power of k. This is totally legit for me to do this because k is a constant. So you would agree with 2 to the power of a constant is in fact a constant. It's just a big constant, depending on if k is big or not. So by the power of a product property, so I'm going to use the following property. By the power of a product property. Now, if you're not sure what I mean by when I say a product of a a power of a product, I'm talking about the following property. You probably can see this on that side. So if I wrote down a times b raised to the power of some exponent m, what I'm saying is that this is in fact equal to a to the m times b to the m. That's what I mean when I write down power of a product property. So hopefully that clarifies that. So I'm going to use this property of exponents right here. So what am I going to do? Well, just notice this. Notice that at both sides of the inequality, I'll just write it here, 2n to the k, which you'd agree with me that this is in fact equal to 2 to the power of k times n to the k, right? So you'd agree with me that this is less than or equal to 2 to the power k times n to the k. For all n greater or equal to 1 are equal. So remember, if you're looking at this guy over here, so remember, this is just really 2 times n, so that's k there, then it's 2 to the power of k times n to the k. So what am I going to pick for n 0? What do I pick? I can pick anything larger than or equal to 1, right? So I could just gonna pick 1. So choose n 0 is equal to 1. Therefore, 2n to the power of k, like this, is big O of n to the k. And we're done. Piece of cake, right? It's a piece of cake. Remember, all the strategy is figuring out what you need to do. So I have to find these two constants. Then I look at the functions and see if there's any property I can take advantage of. In this case, I use this power of a product property of exponents. So that it gives me some intuition of what I can pick for C. I've given you a bunch of recipes in these videos for how to deal with these things, such as polynomials. So this is one standard way of proving this property. And if you know a polynomial is asymptotically non-decreasing, then as a result, then you know polynomials such as n to the k are in fact smooth. Very nice, right?